I'm now going to talk about multi-arm bandits. Now you may ask yourself, what is a multi-arm bandit? Well, essentially it's a system like a one-arm bandit, but you can make different actions by pulling it in different ways. So it's got multiple actions that it can take. And this is considered to be a very simple reinforcement learning problem, and you can look at that in Sutton and Bartow. It is in fact a Markov decision process with a single state, and it's a reward process. So you make an action and you get a reward, or you don't get a reward. And that's what they look like. You've all seen these things in at the seaside. You pull the handle. Depending on the state it's in, it might go to another state and you win lots of money. And the reward is immediate after the action in this particular case, and there is no sequential information. Although there could be, in actual fact, it could be dependent on the state it was in beforehand. But generally speaking, we're thinking of this in terms of no sequence information. You just generate an action and you see whether or not you get a reward. And in this particular game, then, if you're playing one of these machines, you are the agent. You're the one pulling the handle, and you want as much money as you can get, right? So you want to maximise your cumulative reward. We know that if you play these things too long, that you'll lose everything because they are stacked, obviously in favour of the machine. But if you're playing for a short period of time, you may get lucky and end up with some cash. Now, initially, you won't know how to pull the handle of this. You don't know how the action which gives you reward is related to what's going on with the machine. So you need to try things out in order to try to find out the appropriate action to actually get the money. And in order to do that, of course, you need to try lots of things out. You need to explore a bit in order to have a range of actions and relate them to the kind of reward you're getting. So more formally, we think this in terms of, we call it a k-armed bandit problem. It really means it's just got k actions. For each time step, or each time you have a go, for each trial, you can choose an action from one of k actions, right? So written down in this mathematical expression, this little upside down triangle, well, upside down A means for all A, that is a member of this set of values, in this case for this set of actions. And then you will receive a reward RT for a particular time step or particular trial. And we're going to assume now that the reward will only depend on the action. There is no sequential information. That's probably not true, in fact. If you go to most one-arm bandits, it probably does matter what state they're in as to what you're actually going to get from it. But we're going to assume now, for this discussion, that you make an action and the reward you get for that action only depends on the action. It doesn't care about past actions taken. So we're going to assume the reward is what we call is IID, identically independently distributed, and that's something you'll see quite a lot in the machine learning literature. And what we want to do is estimate the action value, right? So you want to know what's the expected reward for a given action. So in other words, this is basically the mathematical expression using the expectation operator. What is the expected reward given action is A? And we're going to write this as Q star of A. Initially, we don't know what the values of the actions are, right? So all we do know is we want to maximize the total reward. So therefore, what we have to do is try things out. We have to try different actions out and learn their values. Then, if we want to, imagine you've now learnt, you've spent an hour wasting your money and you've tried lots of different actions. Then, hopefully, you've got a feeling for what actions generate actually good reward. And then, if you want to get your money back, you might try to just exploit what you know rather than exploring anything anymore. You just try the things you think are the best things to do to give you the maximum reward. So we can formulate this. And we just basically say, we're formulating the action value estimate at time t as, we just say qt of A is approximately equal to the q star of A for all A right? So for all possible actions, this is going to be approximately the case. And we're going to say the greedy action is the action which gives the largest reward. So in other words, it's going to be the action that gives you the largest return on doing something. So if we actually look at this function q t of a, this is giving us the value of an action. So what we say is we want to find the value of the action. We want to know the action that gives us the maximum reward, and we can write that in terms of the expression arg max a. So what that's saying is the max a means we want to find the maximum of this expression, and arg max means we don't want the value, the maximum value coming back. We want to know what the action was. And we'll see this arg max when we discuss Q-learning as well later on. But this is basically just saying we've got this value of each action, and we want to now use this function or this expression that we're going to calculate, and then using that expression we pick basically the action that gives you the largest reward, and it's the actual action we want to get back and not the value that you want to get back. So if we use greedy action, if we're being greedy, we want to exploit the system as much as we can, right? So we want to exploit it. If we know that that's the thing that's giving us the most reward, we should always do that. Now if we don't use greedy, right, we can explore, and I think I've explained this before in terms of, maybe you've got a favourite restaurant, and you like steak, say. Let's say there's a really good steakhouse and you go there a lot because you really think this is a great restaurant and you like the food, but maybe some of the time you ought to be trying out other places. Maybe there's a better place there in town that you've never been to before, so you need a little bit of exploration in order to, if you like, broaden your choices in the future, which in fact may be even better. And it's exactly the same for this kind of thing. Even though we might have a good estimate of what's currently the best action to take, it may be that we haven't tried all the actions out and actually there's a better one out there. So we need to explore to some of the time in order to actually see if we can find something better. Okay. We can't explore and exploit at the same time, right? So you wouldn't necessarily, if you're exploiting, you're doing what you think's best, and if you're exploring, you're just basically just trying something without knowing what the result's going to be. We can't do both at the same time, so quite often what we'll do is stochastically choose to exploit some of the time and exploit and explore the rest of the time. So what we could do is we can use an algorithm called epsilon greedy. So what epsilon greedy does is it's most of the time we're being very greedy and we're trying to do the best thing to get the best reward, but a small probability epsilon, we're doing something just to have a look round and explore. So we can imagine we can do an algorithm to balance this exploration with exploitation quite easily in MATLAB. Just using the rand function, we've done this before, we can say that if the probability is less than epsilon, then we will explore. Otherwise, we will exploit. So rand, don't forget, returns a value from the distribution, a uniform distribution between 0 and 1. So rand less than epsilon will, with probability epsilon, do this expression will be true. So with a small probability we'll explore, otherwise we'll exploit. And that's a nice way of actually building in this exploration mechanism into our learning, and we're going to do that quite a lot in the course, especially in your Q-learning practicals and your coursework. So in this kind of problem we can estimate the value of things by just doing it a lot of times and calculating the average value of each action, right? So we take an action, we look at, for all the different actions, what rewards did they get, and we calculate the average. So what we could do is we could say, for a particular action A, right, the value of this action is the sum of rewards when we took action A, so we've taken action A a load of times. What's the total sum of rewards of taking action A divided by the number of times it was taken, right? And that will give us the average reward for action A, and that's what we want. And we can easily write that down as a sum, because we want, because this is the sum of rewards. So we're just going to say sum between, call it time or trial, time from 1 to time minus 1 of reward, given the action that we've actually chosen. We just sum them all up, and then this term at the bottom is basically just adding up the number of times we took the action. So the sum of the times we took action equals action A. So that's quite nice, and basically when we have a very, very large number of sample n's, then this will converge to basically the value function that we wanted, Q star of A, right? And this is all taken from Rich Sutton. Now, that expression's all very well, but in order to calculate it, we need all the value. We have to calculate all the values each time, right? So imagine we've done n or t trials, or t up to t time in time. We can do that. We can add up all the rewards and divide them by the number that we had. That's not a problem at all. That's exactly what we're saying there. We can also write this though as a sum, right? So we can write it a slightly neater way by saying we don't need this complicated expression with action I equals A. We can just say that's just basically going to be 1 divided by n minus 1, and the sum of all the rewards from 1 to n minus 1. Now what we want to do is maybe just do one more action and calculate what the new value of Qn plus 1 is, right? We want to have one more value coming in, but we don't necessarily want to recompute the whole sum, right? So if we add another value in, then what we end up with, in this case, is it would be, if we calculate the whole thing from first principles, we just substitute here, n equals basically n plus 1, n equals n plus 1, n equals n plus 1. We end up with Q n plus 1 equals 1 divided by n, the sum across all rewards from 1 to n, right? So this is now calculating the whole thing again, from first principles, if you like, over one more trial, or one more time step. So given that we've got the expression now for Q n plus 1, right, the value at n plus 1 is given by this expression, what we can do is we can decompose this into two parts. Let's decompose it. Let's take out, first of all, we take out the factor 1 over n, and then we're going to split the sum up, right? We're going to split the sum up into the last value that we put in, which was the reward n, and the sum of all the other ones from 1 to n minus 1 of Ri. Right, so this is just exactly the same expression. All we've done is we've pulled out the last term and we're adding it on separately. So that's the latest reward in this particular sequence of a set of trials, because we don't really have a sequence as such. It's not caring about sequential value at all. It's just basically just another estimate coming in. And we can say that this sum expression here then, right, is all past reward. That's the sum of all past reward, and this R of n is just the latest reward. So we can start splitting this up again a bit more. Let's now write it in a way so that we can rewrite it again in terms of QNs and things like that. So let's split that up. R 1 over n stays put, R of n stays put, and now what we're going to do is we're going to multiply the top and bottom of this expression with the sum with n minus 1. Right, we're legitimately able to do that because we're doing the same thing at the top and the bottom. But now we're going to start seeing, well, we can actually represent this expression now, this 1 over n minus 1 plus sum between 1 and n minus 1 Ri. We can start representing that in terms of Q of n, right? Because we're now we've got a nice recursive relationship sort of coming out, and we can then substitute in this expression here, this bit, well, 1 divided by n minus 1 sum across 1 to n minus 1 of Ri as Q of n. So let's pop that in there, and then we find that the next, well, the updated action value is given by 1 over n, Rn, as we had before, and then it's n minus 1 Q of n, and we can rearrange that a bit more. Let's expand out this n minus 1 Q of n term, and then we rewrite it again in terms of Q of n plus 1 equals Q of n plus 1 over n Rn minus Q of n. And these should really be little n's. I'll change that in the slides. So we've got this now incremental running average expression that we can use when we actually want to update with a single new measurement, if you like, or a single new trial. So the updated Q value, basically telling us the value of the state, is given by the old value plus 1 over n plus the new reward coming in from the next one, take away what we just had before for Q of n again, right? And interestingly, we look at this update rule and we see it's actually of the same form as things we've been using before in terms of updating things for neural networks and updating things for linear regression, right? So we've got, the form is that we've got a new estimate, right? The new estimate is here yk plus 1. Here it's qn plus 1. In terms of the old estimate, and that will be qn here, and that will be yk here and yk here. A new target value that's coming in this case it's the new reward that we've just got, right? That's the immediate new reward. In this case, it's in terms of the target value. And alpha, right? This here is a 1 over n expression. Here we've got an alpha value. Previously we saw that was a learning rate, right? That's a sort of a scaling factor. So it's just like the update rule for the weights in a neural network. I mean, it's the very basic update rule for the weights in a neural network, right? Because there are much more sophisticated things. But they're basically the same kind of principle. So that's also being used, in fact, when we come to the next stage of talking about reinforcement learning, in terms of being what we call a temporal difference method. It's a running average. So running averages, again, are very similar to the update rules, like I said, for neural networks, and certainly we'll be using them in our reinforcement learning course for temporal difference method. So we can now write some pseudocode for the bandit algorithm. In fact, this is straight out of Sutton and Bartow, and I'll be using their nice little pseudocode inserts like this quite a lot, because it's good to, I find it very, very helpful to look at pseudocode, so I want you to make sure that you can understand it. So the basic idea is, right, we don't know, right, to start with, what the value of Q of n is, or we don't know how many, Q of a, or the number of a. So this is the value of the action, and this is the number of times they've occurred. Initially, we can just set them to 0. We're just initializing these things. Then we're going to have a loop, and this is just going to go round forever in this particular case, because it's just going to keep trying things out, and it's going to be updating. So what it's saying here is we're using, first of all, the thing to notice, we've got this action expression in terms of 2 terms. The first one is taking the best action it can to get the most reward. So it's using the argmax of the value of all the actions. So this is Q of A. If we choose the best action, Q of A will give us the best, the value, which is the best value. Argmax of A will give us the actual action back. So this is choosing the best action given what we know at that point in time about the value function. But it's using this epsilon greedy approach, so it's only doing that with probability 1 minus epsilon. So if epsilon was 0.1, then it would be doing this 90% of the time. And then we have a random exploration part as well. So with probability epsilon, the rest of the time, we're doing a random action. And what you could do with that is if you've got, let's say you've got 10 actions, you'd pick one from a uniform distribution of between 1 and 10. Okay. What we do then is we run the bandit, we give it the action, and we look at the reward, right? So what reward comes back for that particular action? For that particular action, we then increment the number of that particular action we've seen, and then we use our update rule in order to update the value of action. So the value of action becomes what it was before plus 1 divided by the number of times that actions actually occurred, multiplied by the reward we just got, take away the value of the action up to that point. So take away Q of A. And that's very easy to implement. And it's a good thing to look at that very simple example, because Q-learning and all the other mechanisms we're going to look into are very much the same kind of thing.